Hi, welcome to this FMSP online revision recording. In this recording we're looking at Edexcel FP3 and we're looking at questions involving integration. So there's a different video which covers hyperbolic functions and their definition and graphs and questions about that, and also the differentiation of those functions, as well as some other things involving differentiation. This one is purely about integration. So what have we got then? We've got integration of hyperbolic functions and expressions involving them, so you need to know how to integrate cosh and shine. You also need to know how to do integration involving the hyperbolic function. So for example, if we have the integral of 1 over the square root of x squared plus a squared with respect to x, that is equal to inverse shine of x over a plus a constant. So there are a whole load of formula like that you need to know. Some are involving the inverse trig functions, so the integral of 1 over x squared plus a squared with respect to x is 1 over a arc tan x over a plus a constant. Then you've got integration of inverse trig functions and inverse hyperbolic trig functions. So for example, you need to be able to integrate something like arc cosh of x with respect to x. The way you do that is you treat it as a product of 1 and arc cosh x. You can integrate 1, you can differentiate arc cosh x, so you can use integration by parts for that. Using substitutions in these integrals, and for integrals involving quadratic surds, so this is an example, the square root of x squared plus a squared, and other algebraic techniques. Simple reduction formula, this is usually when you have a series of integrals which are a sequence and you can express terms in that sequence in terms of other terms and use that to actually get some integration results. And then there are some standard results about arc length and the area of a surface of revolution, and we'll look at a question like that as well in this recording. So here's our first question. We've got to use calculus to find an exact value of this. It's 1 over a quadratic that we're integrating. There are some standard methods for this. What I'm going to do is I'm just going to start by writing out that function. I'll just write out the question again, in fact. So we have this with respect to x, and what I'm going to do is I'm going to complete the square for the quadratic on the denominator. So we've got the 4 halving to 2, and we consider x plus 2 squared, which of course will give us x squared plus 4x plus 4, so we need an additional 9 to maintain the same denominator there. Now I'm just going to show this in quite a lot of detail at this point. What this reminds me, of course, is this integral I was just talking about, 1 over x squared plus a squared with respect to x, being 1 over a arc tan of x over a plus a constant. So in order to really see that, and you don't necessarily need to show this amount of working, I'm going to use a substitution, which is u equals x plus 2, so that this becomes 1 over u squared plus 9 in the denominator. Du by dx is 1, so dx will switch for du, and I need to add 2 to each of the x limits, so this will become a 3, and this will become a 0, and this will become 1 over u squared plus 9 du. So now I can use this standard result up here to say that this is 1 over 3 arc tan of u over 3 evaluated between 0 and 3. And so this will give me, well, first of all, if I put u equals 3 and I've got a third of arc tan of 1, now arc tan of 1 is pi over 4 and a third of that is pi over 12. If I put in 0, I get 0, so we get pi over 12 minus 0, which is pi over 12. So the most important thing about this is the completing of the square step and the substitution. You don't necessarily need to show all the details of that, because once you've practiced this you will have a different way of setting out, possibly. But that will be worth 5 marks, and we can see how they're allocated in the mark scheme. So there's a mark for the completing of the square step, there's another mark for getting the arc tan part of the integration correct, and then a couple of marks to finish off evaluating correctly, and the final result of pi over 12. Okay, our next question is a reduction formula for integration. So here we've got this sequence of integrals. They're definite integrals from 0 to a of some function of x, and we've got to show that if n is greater than or equal to 2, we have this relationship between in, the subscript powers and involving that, and most importantly in minus 2. So usually in this kind of relationship we need to use integration by parts, because we can imagine that in minus 2 is the same as this, but with 2 less on this power of this bracket. And so we can use integration by parts to differentiate that particular term so that its power reduces by 1 each time in order to get this relationship. Okay, let's have a look at how this might work then. So we have in equals the integral from 0 to a of a minus x to the n times cos x dx. As I say, we're going to use integration by parts. So it seems to me that the thing where we want to reduce the power is a minus x to the n, so that will need to be u, and v dash will need to be cos x. So u dash therefore is minus n a minus x to the n minus 1, and v will be sine x. And if we use the integration by parts formula, we're going to have a minus x to the n, so this is u times v times sine x, and this is a definite integral, so we need to evaluate that between 0 and a and take the difference, and then we've got minus, but of course this times this will have a minus sign in front of it as well, so this is minus the integral of u dash times v, so that will actually be plus, and then we'll leave the n outside as well. We've got a minus x to the n minus 1 times sine x dx, and that will be from 0 to a as well. Okay, so if we look at this term here, if we substitute x equals a, we get 0 because we get a minus a to the n, 0 to the n. If we substitute x equals 0, we also get 0 because sine of 0 is 0, so that's just 0, and we're actually left with this to deal with. Now the n with respect to x is a constant, everything else is a function of x, so I can just write this n here, and now I'm going to look at this integral. So again, I want to get that power down again by another 1 so that it will look something more like in minus 2. So again, I think we need u to be a minus x to the n minus 1, and v this time will be sine x. So that means that u dash will be the negative of n minus 1, and then this time a minus x to the n minus 2, and this will be v dash, so v will be the negative of cosine of x. So if we apply that, and we'll put all this inside square brackets just to be careful, we've got minus a minus x to the n minus 1 times cos x, and again that needs to be evaluated between 0 and a, and then we're going to have minus the integral of u dash times v. So we will have that minus sign there. We'll leave the n minus 1 out at the front. We've then got the integral from 0 to a of a minus x to the power of n minus 2 times cosine of x dx, and that's all in a square bracket, all multiplied by n here at the front. So let's start to evaluate this. So if we put in x equals a, we get 0 here. If we put in x equals 0, we're going to get 1 for cosine of 0. So that means we're going to get minus a to the power of n minus 1, but that's subtracted. So I think we'll end up with n times a to the n minus 1, and then this bit here, we've got our n minus 1 sitting in front, but then this integral is actually in minus 2. Just look at the power there compared to this expression. So we have n a to the n minus 1 minus n minus 1 in minus 2 as required. Moving into part B, we've now got to evaluate this. So if we compare this to the work we've already done, we can see that a is now taking on a specific value, pi over 2, and we've got squaring here. So this is like I2 with a being pi over 2. That's what we've been asked to evaluate. So we have a way of expressing I2 in terms of I0 here. Imagine that n is 2 here, this will be 0. So let's just write out what that is, and let's set a to be pi over 2 as well. So I2, which is what we need to calculate, is equal to, so n here is 2, so it's 2, and then a is pi over 2, so pi over 2, and n minus 1 is 1, so that's just raised to the power of 1, minus, and then n is 2, n minus 1 is 1, times times in minus 2. So this bit here will just be pi, and take away 2, sorry, n minus 2 here of course is 0, so this is I subscript 0, so it's pi minus 2 I subscript 0. So let's have a look at what that is. So if we look at our expression here, that will be the integral from 0 to pi over 2, because a is pi over 2, and n here is 0, so we won't have anything for this, that'll just be 1, and we've just got cosine of x dx. So we've got pi minus 2, and then this integration will give us sine x between 0 and pi over 2. And if we put pi over 2 in, we get 1. If we put 0 in, we get 0. So this will give us pi minus 2 overall. Let's have a look at the mark scheme for that. So we've got a first application of integration by parts worth 2 marks, but connected to later on. We've got that first term disappearing for 0, and then the second application of integration by parts here. Realising that this is I2 with a being pi over 2 and using the reduction formula, and then another mark here for just integrating the cos x bit right as 1, so you end up with pi minus 2 there. Okay, in the next part of the question then, we've got a standard situation. We've got a part of a curve, it's y equals 2x cubed, but just between 0 and 2. So we've got to imagine that that's rotated all the way around the x-axis, and we're trying to work out the surface area generated, giving our answer correct to 3 significant figures. Okay, so there's a standard formula for this. So the surface area that we'll get here, we need to take 2 pi times the integral, so in general it will be between a and b if our curve is defined between x equals a and x equals b. So for us it will be 0 to 2, and it's the y coordinate in terms of x times the square root of 1 plus dy by dx all squared, and that will be another function of x integrated with respect to x. So let's have a look at how this works out for us. So we've got 2 pi, integral from 0 to 2, so y is 2x cubed. Now let's do some rough work over here. So dy by dx is 6x squared, so we'll have the square root of 1 plus 36 x to the 4 dx, and what I'm going to do is I'm just going to move this 2 out to the front. So now we've got 4 pi integral from 0 to 2 of x cubed, and I'll write this as a power a half instead of square root. So we've got 1 plus 36 x to the 4 to the power of a half dx. Now if we look at this bracket here, it does actually differentiate to a multiple of x cubed, so that means we can do this by inspection. We'll leave the 4 pi here. So if we were to differentiate 1 plus 36 x to the 4 to the power of 1.5, what would we actually get? So this is considering differentiation here. So this would give us, we'd have 3 over 2 here. We'd of course have a 4 and a 36, because of when we differentiate this bracket we'll get 4 times 36 x cubed, and then 1 plus 36 x to the 4 to the power of a half. So we just need to make sure we're compensating for all of these values here when we get our antiderivative. So it's going to be 1 plus 36 x to the 4 to the power of 3 over 2, and we need to multiply that by 2 and divide by 3 times 4 times 36 to get that right, and then we'll evaluate this between 0 and 2. So we can pull out this factor here, which will give us 4 pi divided by 216 in front, and then we've got to have 1 plus 36 x to the 4 to the power of 3 over 2, all evaluated between 0 and 2. So we're into some calculator work at that point. If you do that, you will get a value of 806 to 3 significant figures. Let's have a look at the mark scheme for this one. It's only worth 5 marks, so you need dy by dx, you need to use the standard formula, and you're doing some integration by inspection here and being very careful about that. So there are 3 marks for that, and then there's another couple of marks for getting the integration right and using the limit right for 5. So our final question is some more integration. Let's look at part A first of all. So we use a similar technique to one of the questions that we saw earlier. We're going to start with that integral. So it looks like this. And what we're going to do here is we notice that this doesn't factorise. In fact, it hasn't got real roots at all. So we're going to complete the square in the denominator. This is the quadratic in the denominator. So that will give us x minus 5 squared, which of course will give us a plus 25, so we need another 9 to make that up to 34. So we get this, and again I will emphasise what's going on here by using a substitution. It's u equals x minus 5, du by dx is 1, so this becomes, in the new limits, 0 to 3, 1 over u squared plus 9 du, and this is equal to arctan, a third arctan of u over 3, and we need to evaluate that between 0 and 3. So if we put in u equals 3, we get arctan of 1, which is pi over 4, and we take a third of that, so that will be pi divided by 12. If we put in 0, we get 0, so our answer there is pi over 12, and k therefore is 1/12. Okay, let's have a look at how that works. So we can see here that we've got the standard substitution or a direct result using limits of 3 and 0 if you've done the substitution to give pi over 12. So you've got a mark for completing the square, marks for dealing with the arctan integration, and then finishing off and using the limits correctly. Okay, so in part B we've now got a square root there, but we're going to use the same method. We know this hasn't got real roots, so we can't factorise and use some other algebraic method. So again, we're going to look at expressing this as 1 over the square root of x minus 5 squared plus 9 dx. Okay, so this looks a bit like the fact that if we integrate 1 over the square root of x squared plus a squared dx, that's inverse sine of x over a plus c. So again, we're going to make the same substitution here. It's u equals x minus 5, du by dx is 1, so du switches for dx 1 to 1, and the new limits will be 0 and 3, so we've got 1 over the square root of u squared plus 9 du, which is going to be inverse sine of u over 3 evaluated between 0 and 3. So we have inverse sine of 1, this is when u equals 3, minus inverse sine of 0. Now to finish this off, we just need to use the fact that inverse sine in terms of log, so if we want to take inverse sine of x, that will be equal to log of x plus the square root of x squared plus 1. We're using that with x being 1, so this will give us log of 1 plus root 2, and arc sine of 0 is 0, so we have a final result log of 1 plus root 2. So in terms of this, we have a being 1 and n being 2. And if we just look at the mark allocation for that, again it's similar to the first part because we've already done completing the square. We've already seen something similar, so there's one less mark for this, but using the limits correctly. And then of course in this case you need to use that log expression for inverse sine at some point if you're using that particular method. Okay, hopefully that was useful. If you want to look at more of our videos or anything else, go to the Further Maths Support Programme website, and thank you very much.